I'm not sure. I think we can start.
No, let's give some time.
Okay.
Okay, so maybe let's start. I think people are going to trickle in, but in the interest of time for everyone. Thank you for joining the Best of TVLSI webinar series. Today we have a very interesting presentation based on a paper that was published recently in the Transactions on the LSI. The title is, as you see on the, and let us know if you don't see the slides, but title is a physics-informed neural network surrogate for runtime PDN and dynamic droop prediction in 2.5D chiplet integration. Four authors. The first author, Shi Chen, he's going to make the presentation. The last author, Jie Gu, the advisor, he's going to start giving a little bit of context for the presentation. Quick bios. She is a student, member of IEEE. He received a bachelor's from Southeast University in Nanjing, China. And he's currently in a PhD program in computer engineering at Northwestern. And his interests are in mixed signal VLSI design and machine learning software hardware co-design. Jay is an associate professor at Northwestern. He is a senior member of IEEE. He got his bachelor from Tsinghua, master's from Texas A&M, and PhD from the University of Minnesota. He has some experience in industry at Texas Instruments, working on low voltage mobile processor design and power management. And he also was a senior staff engineer in MaxLinear. But now he's a successful, currently promoted, congratulations, Jie, to associate professor. He's on many program committees and associate editor for multiple journals, including TVLSI, and he has also received an NSF Career Award. So, Jay, if you want to start with a few minutes, and then we'll go to the main presentation.
Sure, sure. So thank you so much, Professor Stan, and also Professor Guo for inviting us to give a talk here. So I think he will go into the details, but I just want to give a few just a very quick introduction on why do we do this work. I think I want to highlight is we think there's a little bit overlook on the problem that we're facing here in terms of dynamic voltage droop or dynamic power supply noise. This is because I think in the past there has been a lot of effort putting into the power supply noise analysis from EDA community, but recently we see a lot of papers from industry about dealing with the dynamic condition. For example, the AI workload introduce a lot of fast transients, which cause the supply noise and endanger the timing of the chip. And this is very dynamic in a way that it's real time, very fast, and incur not just IR droop but also inductance noise coming from package. And this problem has been reported as the largest supply noise to the system. So in the past, we see a lot of EDA tools, but the new condition or a lot of new direction that we see in the power integrity community is to do the real-time monitor and real-time management. But for doing that, you need a very accurate, basically, computing solution, but also low cost and fast because we want in real time to deal with them. In that case, a lot of existing solution space may not work anymore, and especially for chiplet condition, when you can see basically the power delivery network has become much more complicated, which he will get into that. In that case, we need a fast, accurate, but also low-cost solution to implement the real-time operation in here. And especially for dynamic droop, we need not only simple kind of nodal analysis, we also need basically PDE, partial differential equation solver, which makes the problem much more complicated. In that case, we see a new kind of machine learning model, the physically informed neural network, actually can provide this kind of solution, and also have in many cases have a better accuracy. So that's what motivates us to get into this interesting model, and also use the model to solve a more complicated problem in the chiplet solution, in the chiplet space. So I think we think this work is pretty. It's still pretty preliminary. There are a lot of further work that can be done. So we hope this work can inspire more people to join in and look at the problem, look at the solution space in the coming future. So with that, I'll give the knob to I'll give the control to He, and He, you can start.
Okay.
Thank you, Professor Jie. You have the, yeah, please go on.
Okay, thanks for the time. Yeah, hello everyone. I'm Xi Chen from Northwestern University. Yeah, thanks for your time to come to attend this Best of the TVLSI webinar series. And we also appreciate this opportunity to share our work to researchers or engineers who are interested in this topic. Today, I'm going to introduce our work, this physics-informed neural network, Surrogate, for the runtime PDN analysis and the dynamic droop prediction, specifically in 2.5D chiplet solution. So here is the outline of my presentation today. I will first introduce the background, the challenges we are trying to address, and the motivation behind our work. Then I will provide the technical details of how we model the chiplet PDN, and how our proposed physics-informed neural network framework. And after that, I will introduce some experimental results corresponding to the features of our proposed scheme. And finally, I will conclude our work. Let me begin with the background and motivation for this work. The chiplet integration is one of the advanced packaging solution that combines separately optimized compute, memory, and I/O IP styles within a single package. Compared with a large monolithic design, the chiplet can provide better design flexibility, the improved manufacture yield and cost efficiency, and more scalable performance. These advantages are pretty attractive for increasing large and compute-intensive applications such as AI workloads. And as shown in the right figure, the market projection also reflects the growing interest in this technology. The global chiplet market is projected to increase from 6.3 billion in 25 to more than 100 billion by 33. Demonstrating both the potential benefit and increasing importance of the chiplet-based systems. Despite these benefits, the chiplet integration also introduced several design challenges. One of the important challenges is the increased complexity of the power delivery network. or PDN. Compared with the conventional single die system, a 2.5D chiplet platform, as shown in the figure of this slide, contains additional PDN layers and interfaces. Multiple chiplets, first of all, multiple chiplets are connected to the interposer through the micro bumps. The interposer is then connected to the package substrate through the through-silicon vias and the C4 bumps. And the package is finally connected to the board. The unique part of in the chiplet is actually the interposer. It may be implemented using either organic or silicon technology, particularly the silicon interposer, which is a more advanced one, is actually due to some similar characteristics to the chip. It has a certain metal density constraint that make the modeling and the evaluation more challenging. It cannot be simply represented by a lumped model. So as a result, this hierarchical PDN increase both modeling and analysis complexity. Although existing EDA tools are powerful enough to provide accurate result, the solver-based transient analysis still remains computational costly, especially as chiplet systems become larger and more workload scenarios are going to be evaluated. The complexity of the PDN has a significant impact on the supply droop. So let me first give a brief overview of the supply droop problem. The supply droop that we are looking at refers to a temporary reduction in the on-chip supply voltage caused by the changes, the workload changes in a digital SoC, as shown on the left side of this slide. Modern SoC covers a wide range of applications and architectures. Their workloads are also vary rapidly during the runtime, as shown in the center of these slides, like those power curves. When these highly dynamic workloads interact with a complex and varied PDN, such as the chiplet PDN, the resulting voltage droop becomes more difficult to predict and mitigate. Without proper management, the supply droop can limit the maximum operating frequency, will require larger voltage guard band and more conservative designs, and ultimately reduce the runtime performance and overall system efficiency. In addition to the workload variation, the actual supply droop is also strongly determined by the impedance characteristics of the PDN. Because of the different section of the PDN will have a different resonant frequency, the voltage response can contain multiple droop events over the different timescales. As shown in the left side of this slide, which commonly refer as a first droop and second droop and third droop, so on and so forth. Usually the first droop determine the worst case voltage. It occurs very quickly and is primarily dominated by the inductive, the LDIDT noise generated by the rapid change in load current. The figure on the right side also shows the variation of the PDN significantly affected the droop magnitude. Therefore, we need both accurate and fast PDN modeling when we're trying to deal with the runtime dynamic supply droop. Next, I will briefly introduce several existing approaches for the runtime droop mitigation. This will cover a few commonly used methods in terms of the droop mitigation. The first one I want to introduce is the clock throttling. This example is shown in this slide is from IBM. The basic idea of the clock throttling is that when a heavy workload is detected, the clock frequency of the digital SoC would be reduced even up to 0, which will lower the instantaneous switching activity and current demand. This can provide a very fast response to dynamic workload and requires relatively low implementation effort, the implementation complexity, because the control of the clock throttling is mainly applied to the clock system. A small trade-off of this clock throttling method is the performance loss, because reducing the clock frequency during the heavy workload scenario will also reduce the computational throughput. Another example is specifically designed for the chiplet-based system. This is the work from Rebellion, and the method for droop mitigation is workload reshuffling. The basic idea is the test vehicle of this work is chiplet-based NPU architecture. And the basic idea of this workload reshuffling is that the different cores for this NPU will be activated sequentially or hierarchically or dynamically. So instead of activating all the units, all the cores simultaneously, the workload will be distributed in time. So this will reduce the instantaneous current as well, similarly to the clock throttling, and therefore limits the resulted voltage droop. This method is actually attractive for large chiplet system because the workload scheduling strategy can be scaled as the number of the chiplets and cores increases. This slide shows one of our previous work on proactive power management for droop mitigation. The key idea here is to predict a supply droop event based on the digital activities before the actual droop happens, and then take actions through a power converter. That is the basic idea of the proactive power management method. The figure in this slide demonstrate our the framework. So firstly, we import the benchmarks programs into the compiler and RTL simulator to extract the digital activity signals. We also perform the power analysis and the analog mixed signal simulation to get the voltage and current response. By combining the digital features and the simulated droop behavior, we train a machine learning model that predicts the future supply droop based on the runtime digital activities. So this proactive power management, the key benefit of this one is we take actions beforehand. So we eliminate the response margin. And also, since we directly access the voltage, that allow us to respond even faster than most of the other methods. Another extension of our power management work, as shown in this slide, is the key extension is the online learning engine we added into the power management system. So the basic idea of the droop prediction and mitigation is still similar, but we added the online learning engine to capture the PDN variation. So the purpose is to adapt the prediction model to capture the potential varied packaging even for the same design. Because it's likely we have a same design, but you will have different packaging solutions. As discussed earlier, the changes in the package resistance, inductance, and other interconnections can significantly alter the droop response. So by applying this online learning, we will be able to use the same hardware, the same model architecture to adapt those variations even after deployment. This slide shows an example that how we evaluate this adaptation, this PDN adaptation. We place the same testing chip in the several different package configurations, like the 7x5, 7x7, 9x9, 12x12. Also, we swapped number of bonding wires that connected the chip to the supply voltage. Those changes produce a different package impedance. and therefore different dynamic droop characteristics. So after a small amount of additional online training, we are able to use the same design to adapt to each package configuration. So this reduces the prediction error caused by the PDN variation I mentioned earlier in previous slides without redesign the chip or a completely new model. Another minor issue that we have just found in our recent study is the coupling issue in chiplet system. So this slide compared the PDN structure of the chiplet-based system with a conventional multi-chip packaging solution. Based on our simulation and study, we mainly have two observations. Firstly, under comparable conditions, the droop magnitude can be larger in chiplet system because the power delivery path includes additional additional components such as the interposer and the micro bumps. So without putting additional decoupling capacitance or other design optimizations, those actual parasitic may increase the overall PDN impedance, which lead to further actual the larger droop magnitude. Second one is the coupling between different chiplets. The coupling between basically the coupling issue, because the multiple chiplets are sharing the same interposer and package, the workload activity of one chiplet can affect the supply voltage on the neighbor chiplets easier than the case in conventional package solution. I use these slides to demonstrate a simple experiment that we have performed to prove this concept. So we divided the different dies, different chiplets into two groups. The first one is the active die with a running dynamic workload. Another one is idle die with no active workload or a little bit small static or leakage current. We refer the droop on this active die as caused by the dynamic workload as initial droop. And the voltage droop propagated from this active die to the idle die is referred as victim droop. And our experiments show that the victim droop is generally more significant in a chiplet system than in a conventional multi-package system. So this result indicates that because of the stronger coupling through the shared interposer and package PDN, the supply voltage of one chiplet is more strongly affected by the workload activity of its neighboring chiplets. So with all of these introductions, I want to briefly summarize the main motivation of this work. Firstly, the heterogeneous packaging introduced a much more complex multi-layer PDN, which makes the accurate power integrity and the dynamic droop analysis more challenging. Secondly, the modern SoC execute highly dynamic runtime workloads. The corresponding current demand changes so rapidly over time. So droop analysis for the real time must be fast enough and to support the timely prediction and the mitigation purpose. Thirdly, the existing EDA tools are powerful and accurate enough, but most of them are primarily emphasize the static IR droop. While usually the worst case droop is dominated by inductive droop, which require like a larger computation cost, and this will make the most of the existing EDA tool make it difficult for them to perform this dynamic droop prediction in real time. Finally, the silicon PDN naturally follows the well-defined physical laws like the Kirchhoff's laws, Ohm's law, or other circuit equations. And those physical constraints can be incorporated into a like machine learning based model to improve its accuracy, data efficiency, or generalization. So let's move to the first, the model need details of the chiplet PDN. The complete chiplet PDN consists of on-die PDN, the interposer PDN, and the package board PDN. So this slide shows the on-die PDN. Its structure and electrical parameters are extracted from the physical design of the chip. As shown in the left of this slide, we represent the on-die power grid as a distributed resistance inductance mesh, potentially with decoupling capacitance at each node. The resistance and inductance values depend on the physical design parameters such as the metal layers, the routing width, thickness, and pitch. The mesh granularity can also be adjusted, depends on the accuracy requirement, so it's flexible. And we model the board and the package with a lumped model based on most of the previous studies and our simulations. While for interposer, things become a little bit different because when it comes to the silicon interposer, which is more commonly used at this stage, due to the metal density and the routing constraint, the power PDN of the interposer is not a solid plane. So it's implemented as a distributed mesh with electrical behavior similar to an on-chip power grid. So we model the interposer using a RLGC-T network, which is commonly used by researchers nowadays. And this model captures the distributed resistance and inductance, as well as the capacitance and the conductance within and between the neighbor layers. This slide shows the overall PDN model for the chiplet system in our work. This model includes the on-die power grids of multiple chiplets, as shown in those purple layers, and the distributed interposer power mesh, as shown in the gray layers, and the lumped package and board level model, as shown in these green planes. These layers are connected through the physical interface, including the micro bumps, through silicon vias, the C4 bumps. An important feature of our proposed framework is that the mesh granularity can be selected independently, differently for each layer. For example, the chiplet and the interposer may require different spatial resolution because they have a different dimensions and grid structures. So by combining those components, we can construct a very flexible grid-based PDN model that we can use to generate the reference simulation data and to support the development and training of our proposed neural network model. Next, let's move to our proposed physics-informed neural network framework. The physics-informed neural network, or we can call it PINN, is a neural network trained with additional physics constraints. The key difference between a PINN and a conventional neural network is mainly in the training process. A conventional neural network learns only from the labeled data, while the PINN is also forced to satisfy certain physical laws governing the system. In our case, this physics law could be some circuit equations like which is derived from Ohm's law or Kirchhoff's law. They are typically expressed in the form of a partial differential equations, or we can call it PDE. During the training, the residue of those equations are included in the loss function as shown in the right part of this figure and minimized through the backpropagation. This will improve the physical consistency and fidelity of the trained model, which is more useful when the model is applied in a real physical system, such as PDN. The electrical behavior of PDN is learned by minimizing 4 major loss components as shown in these slides. The first one is the data loss. is similar to one we used in a conventional neural network. In our application, it measures the difference between the predicted and ground truth voltage and current. The second one, the physical loss, or we can call it the PDE loss, it's mainly from the residue of PDE or any other physical equations, such as the circuit equations in our application. A smaller physical loss means that the predicted voltage or current distribution more closely satisfy the circuit equations. The third one is the boundary conditions, which refers to some specific location in the analytical space, which I will cover more details in later slides. And the fourth one is the initial condition, which usually constrain the state of the system at the beginning of the analysis, which is like time 0 point. So together, these four losses term guide the network to match the available simulation data while remaining consistent with the certain physical constraint of the system, which is the PDN in our case. So to construct let's begin with the PDE loss or physical loss. To construct the physical loss, we first derive the governing equations for 2D dimension. Although the chiplet is in a 3D space, but we start from the 2D to construct the equations for convenience. As shown in the figure, each node is connected to its neighbor nodes through the distributed resistance and the inductance as introduced in previous slides with those modeling method. The node may also include the capacitance and conductance, depends on different layers, depends on whether it's a chiplet layer or interposer layer. We first write the node equation using Kirchhoff current law to relate the current entering and leaving this node. We also have the equations, the branch equations using Ohm's law and the inductive voltage relationship. These equations refer to the voltage difference between different neighboring nodes to the branch current and its time derivatives. The discrete circuit equations will be then converted into PDE residues along either x-axis or y-axis, as shown in the bottom three rows of these equations. This residue captures the relationship among voltage, current, spatial derivatives, and the temporal derivatives throughout this entire PDN grid. So during the training, the PINN will minimize these residues so that the predictions will try to follow these circuit behaviors. We also, as I mentioned, we need to extend the 2D to 3D to cover to support the chiplet solution. So it's pretty straightforward. This is mainly we just need to introduce another dimension, for example, the z direction, and a corresponding vertical current component. The current equation now includes the current derivatives along all three directions, x, y, z directions, and an additional voltage current equations will be also introduced for the vertical interconnections, which actually in our case refer to the TSV, the C4 bump or micro bump between different layers. The overall form remains similar to the 2D case, but we could use different parameters for different direction. For example, the TSV and bumps definitely have different parameters from the horizontal on-die grid or on interposer grid. So with this 3D formulation, we are able to use the model to capture the current flow not only within a horizontal chiplet layer or interposer layer, but also between layers across the structures, as I mentioned, like the micro bumps and those vertical interconnections. In addition to the PDE residues, we also define the boundary condition and initial condition of the system. So boundary condition applies to the nodes, some, as I mentioned, some specific nodes, some specific positions. In our case, it could be the node located at the physical boundary of a chiplet or interposer, or a node connected to an external voltage source or workload current. For example, as shown in the bottom left of this slide, when a workload current is applied at a node, which make it become a boundary node, the current term must be added to this equation. So with this boundary condition definition, we can ensure that the network can correctly capture those external connections or the physical boundaries. On the right side, the initial condition describes the state of the PDN at time 0. Interestingly, in our applications, this initial condition is happen to be the steady state DC voltage and the DC current. So we can leverage the DC current and DC voltage to serve as the labeled data for the initial condition. On the other hand, by applying this DC voltage and DC current in our training, we are able to use a model to capture both static IR droop and the dynamic supply noise. After constructing the 4 loss, oh, by the way, I introduced the 3 loss, but the remaining one is the data loss, which is pretty much same as the normal neural network. So with all of these 4 loss components, the PDE loss, the boundary condition loss, the initial condition loss, the data loss, we combine them together through a weighted summation to form the total training loss, as shown in the left figure. The unified loss function guides the entire optimization process and forces the model to satisfy both simulation data and the underlying physical constraints. It's important to note that these additional physics-based losses are required only during the training, which means once the model has been trained, we only need the inference, which is just the forward path through the neural network. So that those complicated equations is no longer needed. The runtime prediction still remains fast and computational efficient. However, there is a small problem. If we simply adding these 4 laws together or giving a fixed weight, this may lead to a convergence problem because the laws have different numerical scale and potentially different convergence rate. So one object may dominate the training while others may be insufficiently optimized. To deal with this problem, we leverage an so-called multi-objective optimization strategy that balances the different objectives and improve the training stability. The actual problem in this case is that we have 4 losses and they are calculated from different resources. For example, the data loss is based on the voltage and the current prediction versus the simulated data. While the physical loss, the PDE loss, is based on the equation, based on the circuit equation, the PDE residuals. So therefore, their magnitudes and the dynamic range can differ significantly. So if we're using a fixed weights, the loss with relatively larger magnitude may dominate the gradient update. Even those laws are initially normalized because their relatively scale can continue to change during the training. So our strategy is contains many 2 steps. The first one is we normalize each loss using a characteristic scale so that all the objectives become numerically comparable. And secondly, the normalized loss will be adaptively reweighted according to their recent training progress. For example, a loss that is converging more slowly receives a relatively larger weight, while a loss that has already decreased rapidly will receive less weight. So this dynamic balancing prevents any individual objective from dominating the optimization and enables smoother and more stable convergence across all the loss terms. We also introduced a few additional techniques to support the multi-layer chiplet topology analysis and the realistic runtime workloads. The first one is the interconnection matrix together with layer leveling that is used to identify the position of each node, whether a node is in the interposer or chiplet, and whether there is an interconnection such as TSV or bumps in between. On the right side shows the transient modulator. We use this one because the PINN is simply predict a voltage response to single step function, while the realistic workload is sequential step functions. So we perform a superposition like post-processing to get the response to a sequential step functions with this transient modulation. This slide summarizes the completed proposed framework. This whole model received the spatial coordinates XYZ and the time coordinates and the workload of vectors describing the location and the magnitude of the workloads. During the training, the ground truth voltage and current response are generated using the solver-based spectral simulator. We use those data to calculate the data loss, and we calculated the PDE boundary condition, initial condition loss with the differential operator. We also use the interconnection matrix and layer labeling to provide information about the multi-layer PDN topology. The training optimizer will minimize the combined loss with multi-objective optimization method, as I mentioned earlier, to update the neural network parameters. In our implementation, we use the MLP model with 4 hidden layers. And after training, we will discard all the training optimizer and the simulator. We only needed the neural network to perform the inference. Now I'm going to show some experimental results. This slide shows our test vehicle. We get our test vehicle mainly based on two fabricated chips in our previous work, and we extracted the power grid structures of both chips. One is a RISC V processor, one is a convolutional neural network accelerator. We obtain the realistic workload current profiles through the cadence power analysis tool. And as shown in the center of this figure, we put the processor and accelerators with different on-die grid dimensions corresponding to their size. And we put for interposer, we use physical parameters reported in prior chiplet studies materials as summarized in this table at the bottom left of the slides. We also evaluated the multiple chiplet placement and the topology configurations as shown at the top right of this slide to verify the proposed framework remains accurate and robust enough across different system configurations. The first result I want to show is the data efficiency of the proposed PINN. The horizontal axis represents the normalized amount of the simulation data from the solver-based simulator. And the y-axis is the relative error, the prediction error. Because the PINN learns not only from labeled simulation data, but also the embedded physical constraint. So it will require less labeled samples than conventional neural network. As shown in this curve, our proposed PINN can achieve up to 80% less simulation data than a conventional neural network. This is important because generating labeled PDN data with a conventional solver-based spectral simulator is computationally expensive. So with improved data efficiency, we could reduce the the cost of doing the model development and the training. This slide evaluates the effectiveness of the multi-objective optimization strategy. Here, each curves with different colors represent the different loss across in epochs, and the dashed lines, this vertical dashed lines indicate the point at which the corresponding loss has decreased by a certain percentage, for example, 99.9% from its initial value. Without the MOO, the different loss terms converge at the different places and with different rates. And some objectives continue improving while some keep under optimized because of the scale mismatch. With the MOO, the loss exhibit the smoother and more closely aligned convergence behavior. This result demonstrates that adaptive loss balancing enables more stable training and a tighter overall convergence. This slide shows the generalization of proposed PINN to the unseen conditions. This plot on the left side illustrates how the training and the test data are distributed. The model is only trained with a limited range of the data. By the way, the x-axis is the number of the workload scenarios, different samples of workload scenarios, while the y-axis is represented the workload current, the magnitude. So we train the data with a limited range, where the workload will reach up to only 200 milliamp. But the testing will be performed within a range as high as 500 milliamp, which is well beyond the training distribution. Within the training range, both the conventional neural network and the proposed PINN, as shown in the right figure, can achieve reasonably accurate predictions. Once the workload exceeded the training range, the conventional neural network start to degrade, and the error eventually increased to more than 40 millivolt, while the PINN maintain a consistent error, which is around 5 millivolt. Even the testing range is far beyond the training range. This result shows that embedding the governing circuit in physics, such as a PINN, can improve the extrapolation beyond the available training data, which we can also call it out of distribution data. This slide provides a spatial comparison between the proposed PINN prediction and the spectral simulation. These squares correspond to the interposer, processor, accelerator, which is 3 layers in our analysis. This color map shows the worst droop magnitude predicted by the PINN, and the right side shows the corresponding error we observed from the PINN over the ground truth that we get from the spectral simulator. So overall, it achieves around 1 millivolt error over the spectral simulator. So that indicates that the proposed framework can achieve a relatively accurate prediction. And it's not only a single droop value, but also the entire spatial distribution of PDN layers. Finally, I want to show the comparison. I want to show two comparisons. The table on the top shows the comparison between the PINN and the spectral simulator. And we achieve around 300x speed up over the spectral simulator with around 1 millivolt error. And the bottom table shows the comparison between proposed PINN with the prior normal neural network-based works. There are many that convolutional neural network-based method, and there are in total 2 methods we used to compare. Since we don't have the full access to all the resources, so what we did is we re-implemented the architecture of prior proposed method. in our problems, and we evaluate the performance and then compare them. So our proposed PINN achieves the 2.3 times lower prediction error and 7 times faster runtime. So this is mainly because the embedded physical constraint improve the model accuracy, so which potentially allows a smaller and simpler neural network structure. So let me conclude our work briefly. So we proposed a physics-informed neural network framework for rapid power integrity analysis in 2.5D chiplet system. This framework captures both static R droop and dynamic inductive droop, and models multi-layer PDNs, including chiplets, interposer-package, and PCB. During the training, we embed the physics constraint with a PDE format, as well as the boundary and initial conditions, and we apply the multi-objective optimization to balance the different loss terms. The three key benefits of a proposed PINN. The first one is the speed and accuracy. We achieved a 300x speed up over a spectral simulator with a sub-millivolt accuracy loss. Second one is data efficiency. The proposed PINN achieved 80% less training data than the conventional neural network. And third one is the better extrapolation. The proposed PINN due to the knowledge of the physics in the system that allow us to achieve a better fitting for those out of distribution data or unseen data. In our simulation, simulation shows that the 5 millivolt error is achieved of PINN over the 40 millivolt error from conventional neural network. This conclude our work. Thanks.
Okay. Thank you very much. Very interesting talk. So to remind everyone, the only way we can get questions answered is through the Q&A. We are not going to have chat or verbal. So there are already 6 questions in the Q&A. Thank you very much for those who asked the questions. If there are more questions, please keep adding them. So to help everyone, I'm going to read the question, so you'll need to answer. So the first question is, can you please let us know if there are other ways to combine the different losses together, like multiple regression instead of weighted sum? So I guess this is a very specific question about the way you combine the losses through weighted sum, and if you think other ways to combine them would make sense. Yeah. How did you why did you pick weighted sum? I guess any of these. Yeah.
Okay, sure. So the weighted sum is actually the typical format of the loss calculation in the PINN. So I'm not sure if I'm fully I'm not fully understand the multiple regression. I'm not familiar with this term, but I think there are definitely multiple solutions for combining different loss. So there's and the one that we pick, for example, you can use a weighted one, or you can use a adaptive weighted. But I guess I'm talking about the weighted one. But since you are referring to the multiple regression, so maybe we can go offline, because I guess I'm not fully understanding this term.
Yeah. So, and Giovanni, yeah, if you can be more specific, I'm not sure how to, but if you can ask the question, a second time with more details, maybe we'll get there.
Sure.
Another question also from Giovanni. Can you please discuss how do you perform multi-objective optimization?
Sure. I think the basic idea. Let me go back to the slides So here is the basically is we first normalize the loss with their dynamic range, and then during the adaptive reweighting, we just we define some threshold to detect whether a specific loss is convergent rapidly or under optimized. Then we will, based on this threshold, to either increase the weight or reduce the weight. That's the basic idea of this. It's a straightforward and simple method. There are multiple more complicated and fancier method, but since in our case, our work is focusing on the demonstrating the effectiveness of the PIN. So that is not the main focus of this work. Hopefully that will answer your question.
Okay.
Yeah.
Let's go to the next question, slide 31, if you can go there, about data efficiency. Can you restate the computation cost of going from sim iterations from 1 to 9 on the x-axis, and on the y-axis the PIN reduces from 25% error to 10% error, and basically it says that the y-axis labeling is unclear. Yeah.
The y-axis is a relative error, so we use we perform some normalization, so it's not the absolute values, and the simulation iteration from 1 to 9 means the amount of the simulation we need to run to collect the data, which is proportional to the total simulation data that we need. So the x-axis, you can think it as a how much data, training data we need. I'm not sure this 25% to 10% you are referring to. From okay, I guess I got it. So yeah, this is mainly this is kind of the converged error, basically the trend error after during the basically the final. So basically with those certain amount of data, what is the final error the different model can achieve? So the 25 versus this 100 means the PIN can achieve like a 6x better error than the conventional neural network.
Okay, and actually there is we should have probably dealt with this question before the other one, also from Giovanni, because it's also related to the multi-objective optimization. So for the set of Pareto optimal trade-offs in multi-objective optimization, do you focus on the weighted sum for the total loss or the boundary envelope for data loss, PD loss, IC loss, BC loss? I guess, go to slide 32 and be a little bit more specific.
I think in our case, we focus on the weighted sum for the total loss. We don't specifically take care of any of this loss. But as I mentioned, this algorithm level optimization is like a minor focus of our work. So we have a limited effort on this optimization, so which may not be an optimal solution. There could be more space to improve.
Okay.
Yeah.
Okay, let's move on. Slide 33, what is the traditional training? Okay. Was given samples from 200 milliamps to 500 milliamps. Would the advantage of the PIN model go away? So I guess if you change the training,
the advantage of the PIN model go away. So are you saying, let me make sure I understand the question. So are you saying switch the training distribution with the testing? So we training data from the 200 to 500. You are saying if the training data already cover the highest one, can PIN still have the benefit on the lower current scenarios? Is that your question?
I guess I'm not sure. Yeah,
I guess let me assume that's your question.
Yeah.
And I think it's based on because we have similar simulations, the benefit still exists because this is still on-scene data, unless you have a very perfect linearity in your system, which means the problem is very simple. Then probably even the conventional neural network can achieve that. But if you have a complicated PDN, like which may demonstrate not that linear extrapolation, then the PIN will always have benefit over the conventional neural network. Yeah, but to your answer, that on to your question, my answer is yes. The next question is I cannot sound what you know is the actual
Yeah, so how did
so,
you
okay.
use the RISC-V and the accelerator chip? Did
Yeah,
you
yeah. This
generate?
is
Yeah.
yeah, because I didn't provide too much detail on this because we just borrow the physical design of the chip. As you can see from this figure, this is our testing chip, but we are not using any data from testing chip, but we are using the physical design of the basic pre-silicon design, and we extracted it to get all the RLGC information. So that, and then we convert them into a grid with the modeling method I introduced earlier. So I just needed those RLGC numbers and put them into a grid and put them into interposer. That is how I use and also I needed the power profile is also from the pre-silicon, because to be consistent, I use the pre-silicon physical design. So I also need to use the pre-silicon power, which is current and voltage profiles. That is the information I used from these two fabricated chips.
And we are a little bit over time, so I would like to wrap up in the next few
Sure.
minutes. So, related to this workload, so are you actually generating workloads for CNN, or is it random test vectors?
Oh, we use the workload from the benchmarks programs. It's actually from for example, we use a Mi bench. It's
Okay.
one benchmarks. Yeah, it's not a
Okay.
random vectors.
Okay. So again, back to the multiple regression. Probably this is it probably will not be able to answer this because you are, and I'm not that familiar with multiple regression, but I guess this could be a suggestion for future work for you.
Sure. And
Basically, doing
yeah.
this weighted sum with the multiple linear regression, and yeah.
Yeah, I also leave my email address here, so anyone who has a further question, you can send a question to my email address. Let's do that.
Okay, so let's keep it there, and again to be cognizant of everyone's time. Thank you everyone for joining. I hope you'll join future such webinars. I hope this was interesting to everyone. It was definitely interesting to me. Thank you, he and GF, for a very interesting presentation, and good luck with your career, I guess. Thank you.
Thank you.
Thank
Yeah,
you.
thank
you,
you.
everyone. Bye-bye.